Alright, silly people, here's the situation. Uh, so this is the code that Mark Newman wrote. Uh, it's springs.py in the book, and what it does is it sets a bunch of springs with masses on each end, with all the spring constants the same, just being k. And it calculates the amplitude of each wave that each of the masses is going to make, right? Um, and it displays that on a plot. So I'll show you that it runs, uh, and it does. So each of the points on this plot represent the amplitude of a particular spring uh, as it's moving in a wave up and down. And our goal is to 3D animate it so that it properly shows the thing in oscillatory motion up and down with the proper velocity, right? Um, and I'm just going to use a cosine wave to represent the sinusoidal motion as it goes. So that's cool. Let's get started on that. Gonna get rid of the plt.plot stuff. We don't need that anymore. We also don't need to import matplotlib, so let's get rid of that. We'll do vpython as vp though. And let me go ahead and create a canvas here, vp.canvas, with a width equals 800 and a height equal to 1000. That should show up nice in the video. And again, the code runs and it solves for the amplitudes of each of the masses' motion. We have to actually animate the motion itself. And I'm going to start all of the masses at y equals 0, pretty much. So I'm going to create a list of spheres called sphere ls, right? And also a velocity list called vel ls, which is going to represent the velocity I of sphere I, right? And also, let's just create a for loop for I in range n, and we can create the spheres as we go. The x position of each sphere, Newman suggests we place them 2 meters apart from each other. So I'm going to go ahead and create an x pos variable equals 0 at the start. And actually, that's fine for now. No, it's not. We also need a array which is going to represent the the y position of each sphere that we're going to update once we start looping it. But again, they're all starting at 0, so that's going to be a list with a bunch of zeros in it, right? Okay. In here, you append onto the sphere list, spherelist.append vp.sphere object with position argument equal to a vector with an x value of x position with a y value of 0 again. We're also going to go ahead and y.append 0 just because. So 0 here and 0 on the z-axis. Newman suggests also that we make the radius of each sphere about 0.2 units, so we can put that in. We will also make it so that the velocity values gets appended with something. So if a motion is described by a sine wave, x of t equals amplitude times sine of omega t, then the velocity will have an amplitude omega times that amplitude, right? So the initial velocity value is actually x indexed I times what is this guy? omega. Yeah. So that's fine. But we also are going to end up scaling it by some number, because if we don't, the animation is going to look crazy. I'm going to make the scale 0.01, and that is, it's going to look stupid unless we do exactly that, so it's 0.01 for that. So okay, that's fine. I think we're done appending things into the initial conditions, and we can show that the spheres will all show up all in a line once we run it. Uh-oh. I didn't update the x position. X plus equals 2. My bad. Give that a run. Yeah, there you go. There's a bunch of spheres all in a line, not moving yet. We've just set up the problem. Okay, now we can get into the animating bit. So we'll do while true, so it animates indefinitely. We are going to keep on to a t value because it does matter. Going to make the rate 30 frames per second. We're going to update the velocity. So whatever we have for the velocity right now, I'm actually going to copy into a separate list called vel init. So that's going to be vels.copy. That way we can just make it so that the new velocity for each sphere I, so let's run a for loop for I in range n, and also x pos equals 0 out here. Gonna have to add 2 to the end of x pos at the end of that loop, but vels indexed I will now be equal to vel init indexed I times omega times numpy cosine of omega times t, again times 0.01, because again the thing will look crazy otherwise. Gotta scale it down a little bit. Okay, we can update the positions of these based on the velocity. So we're gonna x pos, well, okay, no, the y component then will be updated equals, now that's just, let's just add on to it via vel list indexed I, and also make so sphere equals sphere ls indexed I, so we can update each particular sphere dot position as a vp.vector, which is now going to have the position x position comma y indexed I comma 0, but the radius and the z value don't change. And yeah, it should update the position of each sphere with a cosinusoidal velocity emulating a sinusoidal motion. Okay, it still kind of looks like we're staying still. You know what it is? I really don't need the additional times 0.01 in there because we're multiplying by vel init. We don't need it. We also don't even need omega really. We just need the cosine function. Okay. Give that a go. Ah, see, now that actually works for a little bit. Okay, yeah, it's pretty smooth actually. All of the spheres moving back and forth from their initial values. Notice how the masses do actually have different amplitudes in the motion. This one isn't moving much at all, but the other ones out towards like either side of the spring move quite a bit. And the velocities, they do get faster as they approach the center, but then slow down as they get towards an extreme value, as you would expect. Of course, making it just equal to a cosine function or a sine function is completely arbitrary, and the process is probably more complex than that. But I think it works to see an animation of it, and a cool animation at that. Okay, I think I've yapped enough.